Okay, cool. So now we are recording. Let's get started. So we already covered all the physical properties and stuff, so we're gonna skip that. We already did this stuff, so we're gonna skip that. Where we stopped is ethers and epoxides. So we're gonna pick up there. So ethers, we kind of already talked about. That's when we have an oxygen with two R groups. So this is a general structure, I guess, of an ether. And ethers can be cyclic, so it could be something like this, right? The two R groups are attached in a ring. And specifically, if we have, a three-membered ring, so a three-membered cyclic ether is an epoxide. So all it is a three-membered cyclic ether. And I'm just going to put R prime just to let you know that they could be the same R group or they could be completely different. So that's essentially just what an ether is and what an epoxide is. It's not like anything too crazy, but now we're going to learn how to actually form an ether. So we're going to start out with our trusty alcohol, and I trust that you guys know at this point that this is an alcohol. So if we react an alcohol with NaOH, what are we essentially going to do? In the first step. Oh, sorry, I'm very sleepy today. Alright, so I can also rephrase it. So NaOH, what actually are the pieces of that we're working with? I'll start awkward dancing. We don't want that. Yes, okay. So we're working with Na plus and OH minus. And at this point, we know that Na plus is kind of just a spectator ion. We don't really care about it. We're just going to cross it out. OH minus is the important bit. And we know that anything with a negative charge is a what or a what? A nucleophile or a base. Ooh, excuse me. Yes. Awesome. So anything that's a nucleophile or a base, or excuse me, anything with a negative charge is a nucleophile or a base. In this case, we have an acidic hydrogen right here, ready to be stolen. So this will just take that hydrogen and give the electrons back to the oxygen. And then someone had asked what document is this? So this is the chapter 11 handout, and it's on Canvas. All right, so once we steal the hydrogen, we give an extra pair of electrons to the oxygen. We give it a negative charge. So what is this molecule called? The alkoxide, exactly. And the alkoxide is essentially the conjugate base of an alcohol. Perfect. So once we have the alkoxide, we have this thing. So X stands for what? This might be something that they just assume you know, or this might be something they covered in Orga 1. This one said heteroatom close. It's a little bit more specific than that. It's a halogen, yes. So I'll write that up here. X equals halogen. And so essentially anything with a carbon chain with a halogen on it is going to be an alkyl halide. So, one more time, anything with a negative charge is a base or a nucleophile. Yes, perfect. So, in this case, we don't have any acidic hydrogens for it to take, so instead of being a base, it will be a nucleophile. So, bam. And why did I choose to attack this carbon and not this carbon? Does anyone know? Or want to take a guess? Because it's the one attached to the halogen, exactly. It's the one that has a leaving group, right? So once we attack this carbon, this is going to leave. Someone said they have to go. Bye-bye. All right, so we attack it. And once we attack it, we kick off the leaving group. We end up with our ether. So it's a pretty straightforward mechanism. We call this the Williamson ether synthesis. Any questions about this mechanism? I'll give you a minute if you want to write it down or take a screenshot or whatever. And also if you have any questions. If not, we are actually going to do one more example like this, except we are going to do an intramolecular Williamson ether synthesis. So, we know we have an intramolecular reaction when the nucleophile and the leaving group are on the same carbon. And then before we move on to that, someone had a great question. So they asked, where did the alkyl halide come from? So this is just a reagent that was given to you in the second step. So if he were to ask you a question like this, it would be like OH in step 1, NaOH in step 2, alkyl halide. And you would have to find B. So it'll be given to you. Yeah. You will never have to like figure so like it'll be straightforward. So it'll either be in the second step or it'll be under the arrow, but you'll know. Okay, you're welcome. So all right, when we do the intramolecular, like I said, it's pretty much the same thing except both of these guys are on the same carbon chain. So first step will be exactly the same. We have that OH minus, and it's going to act like a base, and it's going to steal that hydrogen because that hydrogen is acidic. So we give those electrons back to the oxygen. Bam, bam. X stays the same. And we now have an O minus. So at this point, our O minus, we know, can act like a nucleophile. So it's actually going to go ahead and attack this carbon because this is where we have a leaving group. And we kick off the leaving group. And we end up forming this. Ta-da! All right, so what I want you guys to note from this is, one, we formed a cyclic ether, right? And most specifically, in this case, we got an epoxide. So an intramolecular Williamson ether synthesis will always give you a cyclic ether. And sometimes that cyclic ether does happen to be an epoxide. So it's not always forming an epoxide, but it is always forming a cyclic ether. Does that make sense? So I guess the difference is just like any size can be a cyclic ether. So this is a cyclic ether. This is a cyclic ether. This is a cyclic ether, right? But an epoxide is specifically this guy. So let's say we had done this reaction. I should have given you a moment, but that's fine. So let's say I had given you this exact same reaction, but now I had my OH here and I had my X over here, right? We would eventually deprotonate and get this. And when we attack, we would form, I always like to number, so this is a good practice. I like to start from the oxygen, but you can start wherever you like. So I go 1, 2, 3, 4. So 1, 2, 3, 4. And we know that on carbon 2 we have a substituent, and on carbon 4 we have a substituent. So in this case, we get a cyclic ether, but we do not get an epoxide. And yes, someone said to clarify, intramolecular Williamson ether synthesis always gives a cyclic ether. And if that cyclic ether happens to be a 3-membered ring, it is an epoxide. But it's always going to be cyclic because it's intramolecular. It's within the same molecule. You're very welcome. Okay. So we are going to eventually talk about one more way to make an epoxide, but for now, we're going to focus on the more general ether category, and we're going to talk about how to break ethers. So, when we break ethers, we can only do that in one of these two. So, they're going to be stable in something, and they're going to be cleaved in something. Does anyone know which is which? I know that was kind of a wonky way to say that, but like, I'll ask you differently. What are and if you want to take a guess, it's 50-50. Oh no, someone said they can't hear me anymore. Okay. So was it that it just cut out, or you guys still can't hear me? Just cut out? Okay, sweet. So basically what I was asking is, are ethers cleaved in acid or base? What do you guys think? In acid, I totally agree. So ethers are going to be cleaved in acid, and that means they will be stable in base. Perfect. So the order of reactivity, all right, I'm going to say this, and it's a silly way to remember it, but it'll stick in your head. So the order of reactivity for an acid is going to be 3, 1, 2. We'll talk about exactly what that means in a second, but I want you to think, oh, 3, 1, 2, that's a weird order. That's because it's a pain in the ass. Id. So acids are a pain in the ass. So it goes 3-1-2. It's hard to remember. It's a pain in the acid. Yes, I am way too proud of that. It does make me very excited. But you'll hear my voice in your head during the exam. So just remember, pain in the ass is 3-1-2. And someone asked me to say it again because it keeps cutting out. I don't know why it's doing that. Stupid Wi-Fi. But okay. The order of preference for an acid is 3-1-2 because it's a pain in the ass to remember. So 3-1-2, hard to remember, pain in the ass. All right, and I'm sure you guys are thinking like, what does that even mean? We'll go over it in a second. And someone said they think it's just a WebEx issue because it did that for Wes too. It's totally possible. WebEx is a pain. Okay. So if we are all good, let's move on over. Wow, I don't know why it squished it like that. That's kind of funny. Let's just make a new page then, because we don't want our squished molecules. So, don't mind my scrolling. I just need to figure out exactly what I had drawn. Okay. Alrighty. So, we have a what here? What kind of functional group is this? And in case you guys didn't hear me, what kind of functional group is that? Yes, it's a cyclic ether. Is it also an epoxide? No. Cool. So you are absolutely right. This is a cyclic ether, not an epoxide. Cool. And now we have HBr. So what kind of reagent is HBr? And when I say like what kind of reagent, like acid, base, oxidizing agent, reducing agent, nucleophiles, things like that. So what is our buddy HBr? It's an acid, yes. So when we react a cyclic ether with an acid, we said that it's going to break, right? And I mentioned something weird about 3-1-2. Like, what does that mean? So I'm going to write 3-1-2. And basically what this means is the first step of all these reactions is pretty much going to be the same. And Dr. West calls this the activating step. So the oxygen is going to steal a hydrogen and give those electrons to the bromine. And the reason we call this the activation step is because we end up with a positive charge on the hydrogen. So what this means is this hydrogen wants to, we get a positive charge on the oxygen, which means this oxygen wants to break one of these bonds. So it's a lot easier to actually break this ring open. So that's why we say it's now activated. All right, so once we're activated, in our reaction mixture, we have Br minus. And so I'll draw that out and then I'll explain that one more time because someone asked me to repeat it. So basically the first step of every epoxide or ether cleavage is going to start with an activation step. And so we know in the name cleavage, we want to break this somewhere. And we can break it when it's neutral, but if we give it a positive charge, now we know the oxygen wants to break one of these bonds. So having that positive charge makes it easier to break the bonds. The more positive it is, the more it wants to break one of these bonds so it can take those electrons back for itself. And so that's why we consider it activated, because it's more reactive now. Does that make a little bit more sense? Yes. Okay, cool. So now that we have bromine left, bromine has to attack, and I'm going to zoom in a little bit. And so bromine has two options. It can either attack this side and break this bond, or it can attack this side and break this bond. And so this is where the 3-1-2 comes in. So this carbon right here, is it primary, secondary, or tertiary? This one right here. Okay, one person said tertiary. Some people said secondary. Ooh. Okay, so yes, this is one of my tricks, but a lot of you guys got it. So it looks like it would be tertiary because there's 3 bonds, but remember, we're only counting the bonds to carbon. So in this case, there's only 1, 2 bonds to carbon, so it would actually be secondary. If you said tertiary, I totally understand where you're coming from, but does it make sense why we said secondary? Yes? Okay, sweet. So, how about this one? Is it primary, secondary, or tertiary? Primary, I totally agree. All right, so now we're stuck between primary and secondary, and what's the order for acids again? The pain in the ass. What was the order? 3-1-2. Okay, so what this means is we are going to prefer to attack tertiary. If there's no tertiary, then we prefer primary. And if we have no other choice, we attack secondary. So between secondary and primary, we're going to choose to attack primary. So, bam. And I'm going to just move this over so it's like still legible. All right. And someone asked a question, but I'm just going to finish this one little topic and then I'll go back and answer the question. So when we attack this carbon, we need to break a bond. And until we get to chapter 19, we are never going to break carbon-carbon bonds. We're always going to break the carbon-oxygen bond. So we attack the primary carbon, we break this bond, and we open the ring that way. And so, okay, the 2 questions that I got was, what is this, like, the stability for again? And also, are we always looking at the carbons attached to the oxygen? So, yes, when we're doing the attacking, we're always going to look at the carbon directly attached to the oxygen, because this is the only bond we can really break. We're not going to break any carbon-carbon bonds. We're not going to break any carbon-hydrogen bonds. So we're either going to break this one or this one. And so when we're choosing which side to attack, acids are going to prefer tertiary because that's going to be the most stable. And then we're going to prefer primary. And then after that, we pick secondary. So that's kind of what I mean about like stability and preference and things like that. So is it making a little bit more sense? I know this stuff always confuses students, like what I mean by opening up and things like that. So please take a second, look at it, and Okay, I haven't received any questions, so I'm going to take that as like a sign to move on. Okay, someone said wait. I wait. Also, while the person is typing, I am still a little bit blind, so if like I write things a little bit sloppy or whatever, just please excuse me. Okay, so yes, we are getting to that. So the person just asked like what happens after we break it. So as long as we are okay with what bond I chose, we're going to move on to the next step. So at this point, it's very important that you keep track of all your carbons because you have no idea how many times students do the reaction correctly and then they don't count their carbons properly and they get the wrong answer. So it doesn't really matter where you start counting. I like to start just from the like least hectic side. So I'm gonna say 1, 2, 3, 4, 5. And so we know we have a 5 carbon chain. So 1, 2, 3, 4. Oopsie. You know what? It's fine. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. All right. So once we have our 5 carbon chain, we're going to put our substituent. So someone mentioned this in the chat. Isn't there a methyl coming off the 1? Yes, there is. So one of the substituents off of carbon 1 is a methyl. Cool. And then in addition to the methyl, what else is on carbon 1? There's an oxygen, for sure. And that oxygen also has a hydrogen, so we have an alcohol. Sweet. So what other substituent are we missing? Oh, excuse me, guys. So what other substituent are we missing off of this chain? Hint, look at where the nucleophile added. So there isn't another carbon on 5, but there's going to be a bromine on 5. So we attach something here to carbon 5, and that something was a Br. So attached to carbon 5, we will have Br. Oh, excuse me, that was a ugly hiccup. So any questions about what we got so far? Does this sort of kind of make sense? I'll zoom out so you can see the whole thing. I got one yes, yay. I got another yes, yay. Okay, so I will give it a moment if you guys have anything left to write or if you want to ask any questions. If not, we're going to do one more very similar reaction. Okay, so up next we have essentially the same thing, so I'm just going to copy this, except I'm going to add a twist so we're not doing the same exact thing twice. I'm going to add another carbon here. And we're going to say HBr excess. So I want you to walk me through it. So step number 1, what do we think? You know what, that was kind of boring. Let's try again. Okay, guys, step number 1. What do we think? So someone said the oxygen attacks the acid. Yes. Okay. And I didn't mention this today, but does anyone remember what like the key word, like the buzzword is? What kind of reaction are we doing when we activate? And yeah, someone said that in the handout this looks different. Basically, I said I'm going to add a carbon here just to change it up a little bit. Overall, it'll be the same thing. I just think this is a better use of our time. And someone said it's a yes. Okay. So some people are saying what they think it is in the chat, and I agree with you, but also there's a better term for when we add a proton to something. You're probably yes, protonation, exactly. So this first step, all we're doing is protonating. So, oh, that's so ugly. When we protonate, we get what charge? And while you guys answer that, someone said, is it always going to be HBr? It doesn't have to be HBr, it's just going to be H some halogen. So either HBr or HCl, things like that. Wink, wink, nudge, nudge. Most of the time in this class, it's going to be HBr. And yes, we know it's this mechanism when it's any kind of H plus a halogen. Exactly. And then one of you smarty pantses said it's going to be a plus sign, and I totally agree. So at this point, we have the plus sign. What do we consider this now? What special word do we give this? Activated. Sweet. Oopsie. So it's activated. Now, once it's activated, what do we have left in solution?
The excess?
Well, yes, but excess what? The Br, exactly. Okay, cool. So we have Br minus, and then when we say excess, we mean we have excess acid. So let's say we have like a solution of acid, right? We're gonna ignore that for right now and focus on this guy. So what is this guy gonna do? Ooh, okay. So you guys are saying attack, and then you guys were already telling me like which side we're gonna attack, but we're gonna do that together. One more time, just because I know it's a new concept. So we have an acid catalyst. So what's the order for that acid?
It's gonna look for tertiary first.
Yep. So the order will be 3, 1, 2. And we know that this side is primary because you guys told me that last time. And now you guys know that this one is tertiary because 1, 2, 3 bonds to carbon. And so as everyone was saying in the chat, since we have tertiary present, we are going to attack the tertiary side. So we're going to go bam, attack right here. And so that means we cleave this bond right here, and we open it that way. So at this point, we're going to number our chain, and I'm going to start on this side purely because there's a lot going on this side now. So 1, 2, 3, 4, 5. And so let's draw a 5-carbon chain. 1, 2, 3, 4, 5. Cool. Now let's number it. 1, 2, 3, 4, 5. And so let's place some substituents. What goes where? Oh, okay. So a couple questions. Someone said, where did we cleave on the one above? So the one above, we chose the primary position because we were comparing primary and secondary. But here we're going to choose the tertiary one because we're comparing tertiary and primary. And then someone asked, can you start numbering from either side? Yeah, this isn't like IUPAC numbering. This is just arbitrary numbering, so you keep track of how many carbons you have. And I start numbering on whichever side like I'm not attacking, just so I can like keep it organized in my head. You can start wherever you want. I just start on the side I'm not attacking. So the last question was, which way are we going to open it? So if we attack tertiary, we break this bond, and so we open towards the primary. We're always opening towards the less stable side. So that being said, please tell me what substituents I have and where I have to place them. Yes, so 2 methyls and a bromine on number 5. So bam, bam, bam. Correct. And an alcohol on carbon 1. Awesome. Perfect. So are we done? Haha, we're not done because we have excess. Exactly. So what the heck do you guys think excess is going to do at this point? I'll make it green just for consistency purposes. Another cleavage. Okay, good. But what are we going to cleave? Because we don't have an ether anymore. Now we just have an alcohol. Oh my gosh, I've yawned about 200 times today. But Melanie, don't lose it just because I challenged you. You were on the right track, but instead of having like an ether cleavage, what kind of reaction is this going to be? Think back to like Orga 1 terms. And if you guys don't know, that's fine. Blinking, that's totally okay. I just wanted you to think about it a little bit before I kind of gave it to you. So first thing we're going to do is the activation step again. Even though we don't have an ether, we can do that with the alcohol. We're going to steal that hydrogen. Bam. And wow, that's so ugly. Okay, so now we have we have plus. So when we turn that OH into an H2O plus, we made it a better leaving group. And now we have a good leaving group, and we have Br minus. So it's almost going to be like an SN1 reaction, and we're gonna, or excuse me, an SN2 reaction, and we're going to attack and kick off the leaving group. And so we actually get, I'll copy this so the numbers and everything are there. Or maybe I'll just get rid of it. That works too. And all we've done is now replace the OH with another bromine. So the difference between these reactions is if you do not have excess, so you have 1 mole of HBr, you have 1 bromine and 1 OH. If you have excess HBr, you're going to have 2 bromines on your final product. Does that sort of kind of make sense?
So we're basically doing the reaction twice.
Yep, precisely. Makes sense? Okay, cool. All right, and so someone asked, will I be able to upload the completed document? So I'm not going to upload it like an answer key kind of thing because I don't know, it's complicated. But what I have figured out how to do is share this. So I'm still trying to figure out exactly how it works. But what I can do is like share this note so that you guys can go in and instead of like taking screenshots, you can actually like move things around on Notability if you have Notability, or you can just like save it as a PDF if you don't have Notability. So do you think that would be helpful if I like shared it to you as a note at the end of the week? If you just want to say like yes or no in the chat, if you think it would be helpful if I sent it out like a note at the end of each week. Okay, so a lot of people are saying they think it would help, and so I can definitely do that. And so, like, I know a lot of other SI leaders do upload the answer keys, and I know it has its positives, but what ended up happening in previous semesters was I would upload the answer key, and people would kind of like not like I write a lot of things shorthand in the answers, and then people would go back and like when they looked at the notes they would like miss a lot of things, and then they would get super upset that they didn't have all the information. So for that reason I like to send out like the cheat sheets that I do instead of just sending out answer keys, but I can definitely do it this way as well if anyone benefits from that. So thank you for the input. I'll keep that in mind. And okay, we're technically out of time, but this is going to take like 4 seconds to cover, so I'm going to do that. Actually, no, we'll cover it next time. That's fine. It'll just be like 2 minutes at the beginning of class. We'll do both of these questions. All right, so I will leave it at that today. I will stay on here if anyone has any questions. If not, have a wonderful day. I will see you later.